Okay, good morning and welcome all of you to the morning session of the last day of these workshops. And in the morning session, we will have 4 talks. Most all of them are some sorts of review. So the first talks by the Professor Shekhar Chivukula. He will talk about the physics in what was discussed in the Snowmass in US platforms. Okay, Shekhar, thank you.
Thank you, and thank you to the workshop organizers and speakers and everyone here for a wonderful workshop. I have the dubious privilege of turning from 3 wonderful days of science to starting to talk about policy and planning. So my job is to tell you a little bit about what happened at the Snowmass US planning exercise. Okay, so I'm going to start and to set the stage by talking about the last planning exercise, to give you a sense of what the purpose was and what the outcome was, so you can see how that worked. So the last planning exercise actually occurred in 2013, so 9 years ago. It was the culmination of a year-long effort with a conference in Minneapolis, or Snowmass on the Mississippi. The Mississippi River starts in Minneapolis. And during that time, the US community came together. Everyone was invited to participate, and not just in the US, but physicists from abroad as well. There were many participants from abroad. The fundamental way of participating was to get involved in one of the working groups. The areas of physics were divided into topical groups or working groups to submit white papers for consideration by those working groups. And then the topical groups got together and worked before the meeting. And then at the meeting, everyone got together and tried to come up with a consensus. And I use that word advisedly. This is not a recommendation. It's not a prioritization. It's a consensus about the science. What are the important areas of the science? Oh, that's not me, good. The important areas of the science that need to be covered in a future US program. And the time period in particular was sort of the next decade. So how did that go? So it culminated in that meeting. The topical groups wrote reports. There was an executive summary, which you can find at that URL. And that laid out a roadmap of the scientific opportunities that were available. And then that fed into a very important government planning process in the United States, the Particle Physics Project Prioritization Panel, lots of Ps, P5. And this is a subpanel of the High Energy Physics Advisory Panel, HEPAP, which is the primary government committee which advises the US Department of Energy and the US National Science Foundation on particle physics, broadly speaking. There's an analogous body, NSAC for nuclear physics, for example, and so there's a number of these government advisory committees. Now, they had the job of taking the consensus and actually applying some moderate reality filters, actually, to think about budgets, think about what could actually fit into a program over the following decade. And that would feed into scientific research directions for high energy physics, in particular federal funding profiles and requests over the coming decade. So they came out with their report in May of 2014. I think very importantly, they, I think very effectively packaged the science drivers, as they call it, into sort of 5 relatively pithy statements, which I think still stand up pretty well as the sorts of questions that we are interested in. There's some debate, of course, about exactly how you word these and which. The order is not, by the way, meant to be significant, so that's not a problem. They came up with recommendations. They prioritized projects according to various funding scenarios. As you'll see, I think it was very, very impactful in the last decade in actually setting priorities. Now, very importantly, the process didn't end there. It wasn't just that the report was written, handed off to HEPAP, and that was it. The community stayed engaged in the process, and every year after its publication, especially led by Steve Ritz and others in usparticlephysics.org and the user groups from the US LHC collaborations and other collaborations, every year they put together a sort of a 2-page set of talking points about, about the great discoveries and progress that was made in the last year, and re-establishing what were the priorities year by year. And these documents were then used by the high energy physics community during its visits to Congress or the executive branch to talk about and to stay on the same page and stay coordinated with a message about high energy physics. And so it's an ongoing process. How well did it work? Well, so a little bit of US budget talk here. There's the president's budget, which is in purple, and then there's what's actually appropriated in budget speak in the United States. Appropriation means real money that you can spend. Authorization, which you sometimes hear about, that along with 5 currency units will get you a cup of coffee at Starbucks. So the appropriation is the actual appropriating of the funds that can be spent. And here were the 2 years prior to the P5 report really taking effect, because FY 2014 starts in the middle of 2013, right? And you'll see the US high energy physics, this is the DOE budget in particular, US high energy physics budget was around $800 million at that period. P5 was asked to consider 2 funding scenarios, the red and the blue lines, which are they were asked to say what kind of program could fit in those blue and red lines. The actual amounts that were appropriated are these green points. And you'll see that by 2021, the last time that we have a full authorization, that's almost $300 million higher than it was where we started. So especially given the political environment that we were dealing with, I think that's a remarkable success. And so from the feedback that we get when we go to Congress and from the executive branch, the fact that the high energy physics community in the United States was able to establish a priority, stay on message, and talk with a unified voice made a big difference. It's a necessary but not sufficient condition, though, of course, but we need to have that, I think, in order to get to have the possibility of that. Now, this enabled all sorts of, I think, important agreements, including international funding agreements with India, for example, that we heard about, as well as CERN and others, and so that it's important not just for the U.S. physics, but it also set the stage for U.S. collaboration globally. So that was important. Okay, now where are we now? And this is actually a slide shown at Snowmass from Harriet Cohn, who is the associate director of the Office of Science. And this shows in font that's so small that you can't read, different projects that were prioritized by P5. In green are the projects that are actually taking data or doing analysis. This is a timeline going from 2013 to 2024. Blue are, blue are those that are under construction. Yellow are those that are under conceptual consideration and design. And you'll see that an enormous number of projects have moved to the right and from the conceptual design to the actual operation phase. So just so you know that things weren't left out, HL-LHC accelerator upgrade is here, HL-LHC detector upgrade is up here, and so you can see that's firmly in the blue phase, right, moving towards deployment as we've heard. Now, so that was the result, I think, of this exercise of being able to have a consistent message and succeed, I think, in showing that we were worthy of the trust of our fellow citizens to do good science. And in order to have, so where do we go from here? In order to have a good program, you need a mix of projects, right? You need projects that are being conceived, you need projects that are being constructed, you need projects that are doing science. So we have an opportunity here as we come to the end of this decade to plan for the next 10 years about what kinds of projects and what kinds of how we want to structure, in essence, high energy physics in the coming decade. Now, having said that, while the P5 exercise will focus on the next decade, we actually know that we're talking about 20 and 30-year time horizons in some cases. So we have to have some consideration that many of these projects are going to go on even longer than that. All right. So that was the purpose for Snowmass 2021, in a sense, to repeat this exercise, to bring the US high energy physics community together, to arrive, to analyze the scientific opportunities, the progress that had been made in the field over the last decade, and to be able to produce a consensus document that would then go forward into another P5 process and hopefully another 10 years of a robust funding for high energy physics. So that's the goal. Now, you may wonder why this was titled Snowmass 2021, and I'm talking to you in 2022. And the meeting actually happened in 2022. It's because we had a year's delay due to COVID. We actually started the exercise in the summer of 2020. We were all optimistic or hopeful that 2021 we'd be able to still be able to meet in person, be able to conclude the exercise. But of course, globally, the pandemic lasted much longer. And that was particularly difficult for our younger colleagues, especially those who are caregivers who have children. So we took the opportunity to take a pause for 7 months and to we postponed the meeting for 1 year. It turned out that because of the effect of COVID on projects for the funding profiles of things, this essentially was a wash because projects were delayed in many cases by about a year. So we're still roughly in the same relative time. So Snowmass 2021, we had these 10 frontiers. You can read them for yourself. We had 30 frontier conveners, many of whom were international conveners, not just from the United States. 250 topical groups. Each of those frontiers had different working groups. We had inter-frontier liaisons, and we had special early career liaisons. That culminated in a study that happened then, or a meeting rather, in July of this year. And great thanks to Gordon Watch and Shi Su, who some of you may know, who really organized that. They swear they will never do it again, but they pulled it off this year. So just in terms of participation, as one measure of success, we had over 700 participants in person. For almost everyone I spoke to, that was their first in-person conference or workshop since the pandemic had started. I've seen several people here who participated, Frank, for example, and others. We had 650 virtual participants. That's a little bit hard to track, but that's the number of registrations. And they actually had to, if you were a more senior scientist, you actually had to pay something, so it meant something. We had press and local volunteers, so we had almost 1,400 participants. And another measure of success is we only had 35 confirmed COVID cases during that workshop. So people, I think the community really came together and observed masking protocol and all that sort of thing. So what was the output? Well, you've seen much of the output here. I lost track after the first day. I was keeping track of how many times Snowmass white paper appeared on slides, but I lost track. There were over 500 white papers that were submitted, almost 80 topical group reports, 10 frontier summaries that are almost complete. These are written documents summarizing the consensus that was arrived at by a given frontier. By next week, they should all be public on the archive. Roughly half of them are already on the archive. The rest of them should be in short order. And we're very busy preparing the executive summary. Our initial plan was to get all of this done by the end of October. Well, best laid plans, you know how that works, but we should be getting that done quite soon. Okay, Vladimir needs help. Okay. So it's not possible for me in 30 minutes plus 5 to give you a sense of all of the recommendations or discuss all of the outcomes. So I'm going to give you instead just sort of a sampling of them from the different frontiers. These are just diagrams to say that people actually had nice diagrams. This is a dark matter diagram. You've seen a version of this in different talks here. This is the energy frontier trying to summarize the different questions that it can answer. And this is the neutrino frontier showing the wide diversity of effort in different neutrino experiments. And this is actually a timeline, and in type that's so small, even on the full-size slide, you can't really see it. They list all of the different neutrino experiments that people are involved in, just to show that they have done their homework. So let me give you a sense of some of the I will use the word recommendation, but we tried to be careful to talk about these as conclusions. Really, P5 is the one that's ultimately going to get recommendations. Let me give you a sense of the recommendations having to do with the larger experiments in the different frontiers. So the cosmic frontier really had three major thrusts, studies of the cosmic microwave background, spectroscopic surveys, line image mapping, and then, of course, associated but not purely high energy physics is gravitational wave observatories. And they have CMBS-4, the sort of next generation of cosmic microwave background experiments is the next, it's a telescope array, but anyway, is the next big priority of that field that's getting underway. And then they're moving towards the next generation in the spectroscopic surveys and the line image mapping surveys. And this one in particular had to coordinate with the Astro 2020 survey that was also had just been finished. And so we use some NASA speak here. Pathfinder means pilot experiments to actually understand how to build the experiment. The energy frontier is probably the most directly applicable here, so let me spend a minute on this. The priorities of the energy frontier include, fast start for construction of an E+C- Higgs factory. I think that's very much in line with the European strategy study and what we've heard here too. One difference I would point out is that while the European strategy survey, as we heard, has a plan A and a plan B, with plan A being FCCEE and plan B being some other thing, the US community was not willing to make a prioritization of FCCEE over the others. So at this point, the community is interested in pursuing or seeing what can be done in potentially any of these options. But to be ready to really participate, they want to have targeted research and development for detectors at a Higgs factory. So that I think goes quite well with what's going on globally. And then, this sort of goes along with the fact that there are other potential Higgs factories being considered, R&D towards understanding if the costs for a Higgs factory can be lowered and whether it's even possible to site a Higgs factory in the United States, perhaps at the Fermilab site. And then for the longer term, as we have seen, sort of request targeted R&D for multi-TeV colliders as opposed to generic accelerator R&D. You'll see more of that when I talk about the accelerator frontier. So that's the energy frontier, and heavy flavor in rare and precision. At least these are the heavy flavor factories. Continued participation in LHC, both Atlas and CMS, as well as LHCb. Participation in Bell 2, and potentially also participation in accelerators in China. And then, of course, there's a fairly, not shown on this slide, there's a big investment in the US community in mu-to-E at Fermilab. In the neutrino frontier, this one, you heard about DUNE. LBNF DUNE is the highest priority of the neutrino frontier. That project has been divided into two stages, as you've heard. Phase 1 consists of the civil facilities, or rather the excavation at SURF for up to 4 caverns for 4 different detectors. It's the LBNF beamline at Fermilab, the 800 MeV proton accelerator, and a somewhat curtailed near detector program at Fermilab. That's phase 1. The price tag for phase 1 in total, including contingency, is $3 billion. And it's the first, it's going to be the first truly international collaboration in many ways at Fermilab and in the United States. So that's an important milestone. Now, phase 1 is not sufficient to answer all of the questions that we heard about. I think it was yesterday in the DUNE talk. And so phase 2 is the next thing that the neutrino frontier would like to see happen. That includes finishing the far detectors at Sanford, the other 2 detectors, the other half, and finishing the near detector complex and upgrading the proton accelerator to increase the intensity of the beam. So there is a possibility, given the delay in the other 2 detectors at Sanford, at SURF, that the technologies for the other 2 detectors could be different, and they could be better, and they could be better at doing things beyond just neutrino physics as well. So that's being pursued. And then there's a portfolio of small and mid-scale neutrino programs that they're considering. Now, in addition to those sort of physics, experimental physics frontiers, there were other frontiers, including theoretical physics, accelerator physics, and underground physics. Theoretical physics, really, we're looking for commitment, much like was made in the European strategy study, sort of recognizing the importance of a healthy and broad theory program, including aspects of computational theory, formal theory, as well as phenomenology or experimentally motivated theory, and understanding that a healthy ecosystem that supports all of those is important for the health of the field. Accelerator physics, I think these recommendations actually closely align with those on the energy frontier and as well as those in the neutrino frontier. In addition to research on the upgrade of the proton driver at Fermilab, the biggest recommendations were sort of having an integrated future collider R&D program. If we have all of this menu of different colliders, making sure that accelerator physics in the United States is organized in such a way that it explores those possibilities in a coherent way that allows us to actually, frankly, I think, be in a position, for example, when the updated European strategy comes out toward the end of this decade, to be able to actually, participate. And then have an active, continue the active generic R&D program for accelerators as well. In addition to the excavation at, this is the underground frontier, the excavation going on now for the dune caverns, the 4 dune caverns, we have the opportunity at this point to potentially do other excavation since all the, the digging apparatus is already below ground, for example, a 3rd generation dark matter detector or other possibilities. So that's something that the underground frontier wants to make sure is considered and is on the table. This instrumentation frontier recommendation has basically to do with funding research and instrumentation. That's a theme I'll come back to later, but that's their primary recommendation. And then in computation, as we heard earlier, there's a lot of important supporting computational software that crosses multiple experiments and crosses both the design and the implementation and the analysis phase of experiments, and some sort of a greater coordination as opposed to simply having computation associated with each experiment. It may still be mostly with each experiment, but still having a coordination across those areas was felt to be an important priority. Finally, one of the novel aspects of Snowmass 2021 in the United States is the formation of a separate community engagement frontier, which considered a wide variety of topics. Often when one says community engagement, one either thinks about public education or outreach, or perhaps diversity, equity, and inclusion. But as you can see, the frontier actually considered all of those areas. And one of the things that I think is going to be very interesting going forward, and is quite frankly a challenge, is to understand, who's responsible for these different things and how do we actually try to get some of this done. So that's something that we're going to have to work on going forward. So where are we now in terms of formation of the new P5? The last day of the Snowmass workshop, Joanne Hewitt announced that Hitoshi Murayama from UC Berkeley will be the chair of the next P5 panel, taking over from Steve Ritz. The plan. So we don't yet have a charge. Any official subpanel of the High Energy Physics Advisory Panel has a charge which defines the questions and the scope of their deliberations, the questions they consider in the scope of their deliberations. We don't have that charge yet, as I'll explain in a minute, but this was Harriet Kung's sort of recommendation of the sorts of things that she thought that P5 should consider. And I want to point out here that this one in particular, a research program to deliver science, I think is a very important one. You might wonder, what is research doing in a particle physics project prioritization panel? Well, what's happened over the last year, you saw that 30% rise in the budget. That was wonderful. But with our emphasis on projects, in many ways, what's happened is the research part of the portfolio for theory, for accelerator and instrumental development has deteriorated in actual real dollars, not in nominal dollars, not just inflation adjusted dollars. And so there certainly was a very strong consensus of our community. There needs to be a balance between those things, because those things form the basis of being able to do the projects and do the science in the long term. So there has been some actual recent good news since Snowmass, just to say we don't all have, it's not all bad news. The somewhat mysteriously named Inflation Reduction Act had $304 million of appropriation. Again, I put that in all caps because that's real money. $304 million for high energy physics that can be spent immediately and is for the next 5 years, over the next 5 years. So that's going to be used in various ways. I don't yet know, there's going to be a HEPAP meeting in December. I think we'll find out more about what high energy physics is doing with that. I would say this doesn't even include, I forget how much is coming to EIC, 60 million or something for the Inflation Reduction Act. So there's another separate amount that's going to EIC also from them. There's and then the CHIPS and Science Act, along with other things, recommends increases in NSF and DOE. That's more on the authorization level. That's a promise. That's not actual money. Okay, so this was the original plan to have everything, have nominations actually were due August 22nd, and to start deliberations. P5 was supposed to start deliberations this fall. Everything got delayed for reasons that will become obvious in a moment. The charge itself, for example, has not yet been settled, and it will be, we think, unveiled at the next HEPAP meeting on December 8th. So that's sort of the next step. Once that's done, I think the panel will be impaneled in short order. And while we may not be able to finish by summer, we hopefully to be able to finish by early fall, if not before. So there's been a major change in the personnel. Thank you. There's been a major change in the personnel overseeing high energy physics at the Department of Energy. Jim Segrist, who was the director of the Office of High Energy Physics, retired, and Gina Ramika from Fermilab is going to be taking over, and took over, I think, on November 8th, so a week ago. So that's the part of the reason why things were delayed, and so we expect now things to move in a more normal schedule. That's not all. We can never do things in ones in the United States. We either do none or 3 or 4. So we're doing 3 this time. There's also an international benchmarking subpanel, which is, I think, among other things, considering, for example, how good a place is the United States to do international collaboration. If we're going to be a host nation for a real substantial international collaboration, how can we be better at that? And what are the characteristics of the field we need to work on for that to happen? Also, the National Academies of Science every decade does a survey of particle physics, and they have been looking carefully at our Snowmass output, and we'll be using that. But their report presumably won't come out to 2024, so that's coming. I'm going to go over these quickly. I've pretty much said all of these. I mean, I think the lessons from the last P5 process were that a consistent message from the community that really is coherent is extraordinarily important and has the opportunity to actually get funding with it. And in the coming decade, we really need to understand how to balance our focus on research with that on projects. The plan, there's continued strong support for the plan that was established, HLLAC, Dune Phase 1, LSST, among others. So I think it's fair to say the last plan succeeded, and that we have the elements of a new successful plan, and that's what we have to execute on now. There are some US-specific issues I think we need to address. I can talk about those later, but you'll have those in the slides, because I wanted, Rohini asked that we think a little bit about the topic of this actual workshop. So with that in mind, I have a few preliminary thoughts and questions about the high energy physics program in India. I should say these are really questions. This is not, by no stretch of the imagination should this be construed as conclusions about anything. I'm just trying to raise questions that I think might be interesting to discuss. And but I have the benefit of really learning from the excellent participation presentations we've had here. Now, in the near term, where near term now means the next 10 years, I think the US and Indian HEP program are very well aligned. I don't can't imagine them being even better aligned than, we've seen the priorities, HL-LHC and LHC, LBNF Dune, Bell 2. We've seen those are exactly the same priorities as the US program and the European program too. I think everything is very well aligned. And I think that the sort of poster child, if you wish, of a really fruitful collaboration that we're having between the United States and India is the sort of PIP2 800 MeV proton driver, where you can see that you saw this slide with all the contributions from India. I think that's extraordinary. And the question then is really, how do we maintain and grow these kind of fruitful global collaborations in the face of the rapidly changing and fluctuating domestic and international conditions that we're all seeing, right? I think that's a challenge. In the intermediate term, global Higgs factory, we heard this during the Linear Collider Accelerator talk, right? How can we resolve this chicken and egg problem that has plagued the ILC? After you, Alphonse. If you go forward, I'll join you, but you won't go forward if I don't. Okay, so how do we get out of that? And in many ways, I think that that really is going to be the central issue for us in the intermediate term globally for high energy physics, right? How do we move forward on it? And our future really does depend on it. In the long term, now here's this slide. This was actually a slide that Fabiola Gianotti showed at Snowmass of FCCEE, and it basically was shown here as well. And you'll notice that the sort of, depending on your point of view, this is optimistic or pessimistic. The start of FCCE operations is the middle of this century. You tell that to somebody that's a postdoc or a graduate student, and they say, I'm going to be older than you are now, right? So how do we collaborate to create a vibrant global program that retains the brightest scientists and provide them with the continuous scientific and professional opportunities they're going to need over the next 50 years, right? I think that's going to be our long-term issue that we have to solve. Now, rather than ending on a downer, let me just say, these are really difficult questions to answer, and luckily we don't have to do these today. We don't have to answer them at 4 o'clock. And I think it would be bad, actually, when you're planning for the next 3 or 4 years, okay, so maybe you have a prospect of really doing a detailed plan. If you're planning for the next 50 years, the future is built incrementally, and it's determined often by contingencies we don't even see now. And we've had no better example of that than the last 3 years, right? With COVID and Ukraine and other things. Nonetheless, I think we understand that having strong scientific priorities, doing the work and the basic research that we need to be able to take advantage of opportunities as they arrive and move ourselves in the right direction does have, I think, the prospect of succeeding. And so that's what we really need. In addition, I think it's especially appropriate to say here that our past successes were built on global scientific and human connections, right? If I just did a little bit of Googling, right, for collaboration between India and CERN, right? There's an agreement back in 1991, which sort of a major formal agreement between the DAE and CERN, and associate membership in 2016. With the United States, collaboration goes even further back. We heard about it, but this sort of Project X collaborative agreement in 2011, we've seen the fruition, or seeing the fruition of that now, 11 years later. With, it's going to continue for the next decade for building the proton driver. So these are the kinds of things I think that really help having, a collaborative and a coherent scientific vision that's backed up by the connections that actually allow us to work together is, I think, extraordinarily important. And I think this workshop is a great example of that. So with that, I think I will conclude with a picture of a mountain.
Thanks, Karan. Excellent talk. I do not think that you expected the better talk in 30 minutes to confine this to Snowmass summary. Yeah, now the floor is open to the question.
Do you know the timeline for the Higgs factory, if at all it happens in Fermilab, or is it you have to wait for FCC decision before you?
I think that's really going to be up to P5. So I don't expect this P5 to make a decision yes or no on Higgs factory. I expect it to make a decision that says, here's how the US is going to pursue a coherent program which will support a Higgs factory, either at FCCEE or in the US. And I would very much want them to be able to be in a position when the European strategy update occurs and there's other developments at CERN for the US to be able to make a rational response. I don't know what that rational response would be, but I think that will happen.
Okay, yeah, so I have a questions and a comment. Questions concern how is the interfacing of the, the Snowmass process for the particle physics side with the nuclear physics and the astroparticle, I mean, things beyond collider, beyond. So how's that happened in the process and, sort of.
So you want me to answer that question first?
Yeah.
So the answer is it is happening. It could be better than it is, but one way it's happening is our steering group includes people who are formerly heads of the division of astrophysics, astrophysics and in APS, nuclear physics, accelerator physics, gravitational physics. There were collaborations, especially among the cosmic frontier, in the case of astrophysics. There are very close collaborations with those. On the nuclear physics side, it's kind of an interesting question. There are some institutional barriers because in the Department of Energy, nuclear physics is one division and high energy physics is another. So for example, neutrinoless double beta decay, which is, I think of it as particle physics, but it belongs in some sense to nuclear physics in DOE. And so we invited the DOE representatives from nuclear physics to come and talk to us, and they have a lot of goodwill to work together. And I'm hopeful that with Regina Romika as the head of the division, that at that level there'll be more coordination. So I think in the process and in the community that coordination can happen. I think there are some issues structurally that we have to address.
Okay, so comment is just about 2 slides back. Right. I mean, anyway, I think this is something probably will be discussed in the roundtable thing. But as far as part of being the community, I think we should be really on the Indian side. I mean, our approach should be not like plan A and plan B. It should be machine agnostic. I mean, whether it's FCCEE or ILC, CPC or whatever, our approach should be more like, wherever the science come, and we have to be prepared on that matter. So
I think we'll be discussing that. Yeah, good.
I'm curious to know about the stand regarding the CEPC machine. If it comes out, will you join or?
That is a fascinating question that I think will be out of our pay grade. I think it will have more to do likely with the international situation and relationships between the two countries than purely the science. I wish I could say it would be otherwise. I think there's the possibility. If we had the example of the Cold War, we know CERN played a crucial role in as being a bridge between Russian physicists and Western physicists. And so I think we have the opportunity in science, if we can navigate the sometimes treacherous international relations waters, to maintain that connection, those connections between. I've certainly done, for example, a lot of collaboration with physicists in China. I know many people have. That's much more difficult now. I literally can't be sure that I can go to China. Actually, they're closed right now because of COVID, so no one can go. But or have them come here. But we can continue to maintain contacts. I think it's going to be driven by things that are outside our control more than the science. I would like it to be like that was said. Wherever the physics is, we go there. But.
Okay, thanks. Yeah, so there's more question maybe he will be in the panel, so we can have a more discussion during the panel sessions. Okay, thank you.